Hello everyone, welcome to Physics Match. Dear students, here we have an interesting problem which can help us to develop some new logics which we can use as a framework to solve many such kind of similar looking problems. So I hope this helps you out. So let's get started. Two masses, small m and capital M, are placed on a frictionless table. Mass small m is projected with speed u0 towards capital M, which is initially at rest. All the collisions are elastic and small m is much smaller than capital M. Initially, small m is at the rigid end. So they have given distance of capital M from the rigid end is small x, and u0 value is being very high value that they have mentioned, and x0 is really small. Make necessary assumptions. Make Mark the correct options. That's what we have. So we need to check out the speed of small m as a function of x, speed of capital M as a function of x. We need to find, and speed of capital M after long time, that we have to check. Then total impulse on the system. Okay, first let's think about what is happening with the system. So here we can easily observe that at t equals 0, we have the particle being here where small m is at the rigid wall and capital M is at x0. So since the given story is as the small m goes and hits this one, the capital M starts moving slowly towards the right hand side. And why I'm saying it is slowly? Because capital M is too massive when compared to small m. So we are considering the velocity of the big M, right, being really small. This will be a small quantity, okay, small value. Now, once we get this logic, we will continue. So we'll have the small m particle which will interact with the capital M. And as capital M is now moving, say with Vm speed, then the small m has to return back with a speed v, say, and if this is the speed with which it is coming back and hitting the wall again it is returning back. Suppose at any given moment, if m is at a distance x away from the wall, then the time taken for the small m particle to go back and hit the capital M, the time taken, if we call that one as a small time taken, mm, I'm calling small time taken because we know that the speed with which the particle small m is traveling is very high. So small time taken for it to go back and hit the wall and reach the capital M is going to be 2x by v. Okay, so this is a time taken for one collision. Suppose if we invert this like 1 by delta t, which is nothing but frequency of collisions, meaning number of collisions that can happen per second. But you might be wondering, sir, this happens and speed keeps changing. Yes, speeds keep changing, but we are considering that the collision frequency depends on the speed. So here the collision frequency, if v is the speed, then it turns out to be v by 2x. This is a collision frequency. Okay. So since v itself is changing, the collision frequency will also keep changing, and the value of v is sufficiently large, and x also changes accordingly. Okay. So this is one of the information we got, like equation 1 and equation 2. Let's keep them for our reference. Now, when it comes to this capital M interaction, imagine that capital M is moving with some Vm speed and the small m is reaching it with a speed v, let's say. Suppose after the collision, if this, say, changes its direction, right? So let's say it is going back with v dash speed after the interaction. Then since capital M is much massive than the small m, let us assume that Vm is not changing much. Okay. So during this elastic collision logic, we know that velocity of separation to the velocity of approach, so which is v dash plus of Vm, this velocity of separation to velocity of approach, which is v minus Vm. This should be equal to 1 since it is elastic collision. Okay. So we can write this one as v minus of 2Vm, right? So V dash will be this value and V dash minus V is going to be minus of 2Vm. So it is just the information that, so change in velocity of the small m block, right? Small m particle it's going to be minus of 2 times of Vm. Okay, now this is again an important relation. Okay, now once we get all these three relations in place, then we will just explore more about how to get information of speed of small m with respect to the distance x. Okay, so we have here change in velocity of the small m block, that is equal to negative 2 times of velocity of the capital M. Velocity of capital M is nothing but rate of change of its position with respect to a reference, that is rigid wall, let's say. So dx by dt, let's say, right? Okay. So using our collision frequency here, we can write minus 2 delta x as it is. We can write 1 by delta t as v by 2x. Okay, v by 2x. Now, using this differential equation, we can just modify this and write it as dv by v. So we can write dv by v is equal to dx by x. dv by v equals dx by x with negative sign. Okay, now we'll put in the limits and we will complete this. So we'll have dv by v equals minus of dx by x. Given story is like initially the particle was thrown with a projection speed of u naught, and at that point the bigger m was at x naught distance away. Then after some time, like because of the collisions, if it is moving with certain speed and the position of this bigger m, right, that is at some x distance. So we have here 1 by v, this can be written as ln v and v naught. Just integrate this, we'll have ln x x naught. So we can write it as ln v naught equals ln x by x naught, v by v naught being equal to x naught by x, just simplification. So vx equals v naught x naught, right? So this is a powerful result, and we can just memorize this result as a standard result for all these kind of problems. Okay, so when this will work, when capital M is much bigger when compared to small m, and you can consider this one as a rigid moving wall also. Okay, in such cases it will work, and we should also know that V naught is sufficiently large value to begin with. And once we recognize this, then V and X product should be constant, meaning as X increases, the distance of the bigger block from the wall increases, the speed of the smaller block keeps reducing, and it is inversely proportional. And why this is happening? Because every interaction with the bigger block, it keeps losing the momentum. Okay, and this is what we are getting. Okay, once we get this logic in place, then V equals V naught X naught by X. Now we will think of the options. We need to first find out the speed. Okay, I was using V naught. The actual initial condition is U naught, right? So let me make it as U naught. This is U naught X naught, right? So this is U naught X naught by X. We will consider the first option and it is correct. Now let's think of the second one. So speed of capital M as a function of X. So speed of capital M as a function of X. This is fine. Now, as we know that we started this particular event with an initial energy of half m u naught squared. This is the entire kinetic energy of the system as we begin with. Then we know that at any given point, the small m will be carrying v squared, this much of kinetic energy, and the rest of the energy should be carried by bigger block, right? So bigger block speed squared, right? So we have to just simplify this. We can write it as m times of u naught squared minus v squared by capital M is vm squared, right? So let's substitute the value of v squared there. So it will become small m by capital M. So I'll take u naught squared outside. It will be 1 minus. If I take u naught squared outside, so it is x naught squared by x squared. So this is about vm, and we can take the root of this and that is our Vm value, which is root of small m by capital M 1 minus x naught squared by x squared. So this is velocity of the bigger M with respect to ground frame. So even second option would be correct. Okay. Then the third one, speed of capital M after long time, right? So after long time, meaning x keeps on increasing, right? After long time. So x shoots up to infinity, let's say, when x becomes very large. When x becomes very large, then we can write Vm, speed of the bigger fellow, right? That becomes u naught root of small m by capital M, because this term will tend to uh, be negligible. So it is u naught root of m by m will survive. So that would be our answer after very long time. This will be the velocity of the bigger m, and we got that here as well. Okay. So A, B, C are correct. And total impulse on the system we need. Total impulse on the system if you want. Let's complete this. Total impulse on the system. Now see, after long time, the capital M will be moving with the speed of u naught root of small m by capital M. And because from the expression, if you see, small v is equal to u naught x naught by x, right? After long time, then at x being equal to large value, v tends to be very small because as x becomes very large, right? So it will be almost considered as 0. Got it? So if that's the case, then small m will be almost having 0 speed, okay, after very long time. So final momentum of the system, if you see, it will be capital M moving with Vm, right? And small m was not moving at all, right? Like, so we ignore that momentum. So m times of u naught root of small m by capital M. This is what we have final momentum. Initial momentum to begin with, small m was started with u naught speed, right? So this was our initial momentum. So total impulse on the system is going to be final momentum minus initial momentum, which is u naught root of small m capital M, just simplification of that, minus m times of u naught, correct? So we can just write u naught times root of small m capital M minus of small m. So that's the total impulse. Total impulse. Okay. So here 2u naught small m plus root of small capital M small m. So definitely this is a wrong option. So this is it, guys. So the takeaway from this particular problem is I want you to remember this result. So Vx is equal to u naught x naught being equal to constant. So that's the takeaway. Now you can see like there is a problem which was asked in JEE Advanced 2019. So probably some of you would have tried this problem. We have a small particle, mass m, moving inside a heavy hollow straight tube along a tube. The of the axis undergoes an elastic collision at two ends. The tube has no friction and it is closed at one end by a flat surface while the other end is fitted with a heavy movable flat piston as shown in the figure. When the distance of the piston from closed end is L equals L naught, the particle speed is V equals V naught. The piston is moved inward at very low speed, capital V, such that capital V is much smaller than dl by L times of V naught. dl is infinitesimal displacement of the piston, which of the following is correct. See, if you have not tried this one, now you can try it and try to use what we have learned in the previous section. Okay. Uh, Suppose if you already have tried this, then this problem is pretty straightforward now, because see, this is similar to the previous problem. This was that rigid wall, and this is a moving heavy mass, let's say. This is like capital M, which is moving with like very slowly. That's they have given. And similar to this one, the position of this bigger M with respect to the rigid wall, right? That is changing. So like x is changing. So L equals L naught, right, to begin with. And initially, when L equals L naught, V is equal to V naught, it seems. So it is more like the previous problem, but in a reverse way, right? Because here it is moving towards the wall. So I would recommend you to try this one if you have not tried. If you have already tried and if you want to check out like your approach, then you can easily do it. Now, since I said you that we can use the direct result once you can see that the same framework is there in the previous problem and this problem. So velocity of the particle, this particle, velocity of small m times the distance of the bigger m, which is piston from the wall, that should be constant. Okay, and that constant should be equal to v naught times the original location, right? This was constant. This is what we have learned from our previous section, right? Now once you get this, then after each collision with the piston, the particle speed changes by 2 times of v, and we got this particular result from equation what 1, equation 1 or 2 or before. Yeah, so I think here we got equation 3. In equation 3 we got it. So we know that magnitude wise the first option is correct. It is 2 times of v. It increases by that. So there it was decreasing, so minus 2v. So here it will increase because here it is pumping energy into it. So I think you can able to relate it. There it was losing speed, here it's gaining speed. There it was losing speed because there it was continuously transferring momentum. Here it is gaining speed because it is gaining momentum from the wall movement. Okay, so that's a essential difference. So A is similar logic, you got it. If the piston moves inward by dl, then the particle speed increases by 2v dl by l, it seems. So we'll just check how this work. Now suppose if you remember this result directly, then you can just say like dv, just derivative, right? dv into x plus v into dx should be equal to 0, right? So we can write now the changes happening to the speed, right? So changes happening to the speed is equal to minus of v dx by x, minus of v dx by x. So here we were expecting the change in speed, right? Here the speed will increase. Speed will increase, and we know that magnitude will increase, and dx here is going to be change in x is dl. So dl is going to be negative dl because l is decreasing, right? So it is negative dl change in x, and x value is just l. So what we expect is the increase in speed, right? It should be v times of dl by l, correct? But here they have said 2 times of v dl by l. So this is going to be wrong option. So the correct option for this one would be v dl by l. Okay. Then the particle kinetic energy increased by a factor of 4 when the piston is moved inward from L naught to L naught by 2. So this we got. So first part we got. So part B we proved it from this one, and part C we will check. So from our given relation, if Vx is equal to constant, then initially this is V naught and L naught is the distance. Then later L naught by 2 is the distance, it seems, for the piston with the wall. Then the speed is going to be the new speed. That new speed, let me call it as V dash. So V dash is going to be 2 times of V naught. So from this we know that kinetic energy of the smaller particle, right? So initially it was half mv naught squared, and the new kinetic energy, suppose if I write ke dash, so it is half m 2 times of v naught the squared, so which is 4 times the initial kinetic energy, right? So with that logic we understood that c, the particle's kinetic energy increased by a factor of 4. The piston is moved inward from L naught to L naught by 2 is also correct. The rate at which the particle strikes the piston is V by L, it seems. So this is rate at which the particle strikes is nothing but collision frequency. And collision frequency we got from the expression that from equation 2, it is V by 2x, correct? So collision frequency, what we expect here is V by 2 times of x. So here they are saying it is V by L. So what we supposed to have for correct answer is V by 2L. But here they are just saying V by L. So it's going to be wrong option. So I think if you remember the results of the previous problem, right? So these kind of problems, like similar looking problems, you can directly answer it and save time. Okay. I hope you like this one. And if you have liked it, please like it and share it with your friends who are preparing for advance. Thank you, everybody. Thanks for watching.